Good afternoon. My name is Chris Ruskowski, and this is a presentation on our homework assignment number 3 from Semiconductor Devices at USF for the fall 2015 semester. For our homework assignment, we were given a metal oxide semiconductor capacitor with some given values, and we were asked to solve for certain parameters. For brevity, I'm going to go ahead and go through some of the earlier stuff without getting into major detail. Suffice to say, we were asked to solve for the capacitance, the Fermi level, the threshold voltage, and the depletion width. As you can see, so far, here are some of the values that popped up on the screen. I do want to pay attention to that when we apply a positive voltage to the gate, we're going to bring electrons to the surface, which will cause band bending. Here, we calculate the threshold voltage as twice the Fermi level. Also, we're going to have at threshold voltage maximum depletion width, which is calculated as with this formula and as such off to the side. All right, moving on. We have the metal semiconductor work function. This is actually a summation of energy states of the different materials. Here we have a simplified flow chart for the material that we were originally given, the PE poly for silicone. This is a very quick, dirty, fast way. The actual derivation requires knowing the electron affinity, the energy states to the vacuum level for every single device, adding them all together, and then we will get close to what this chart references as well. Here, with the chart, our semiconductor work function came out to be 0.3 volts. Moving on, because of the metal work function, we actually do have charges inside of the oxide layer as well as charges induced into the metal and the semiconductor. As such, when we put the three devices together, there will be band bending. To counteract the band bending, we have the actual voltage flat band, the amount of voltage needed to make all of the bands flat. Here, with the calculation, it's basically the charge density of internally to the oxide divided by the capacitance minus the work function, calculated as such. Moving on, we then want to calculate the actual voltage threshold that we would need to apply. Before, we had the ideal assumption where there was no charges and no energy states that we had to account for. After we have to account for everything, we have basically the flat band voltage plus the voltage potential at the surface plus the charge density of the depletion with the divided by the capacitance of the oxide. This will give you the more realistic assumption, a realistic solution that the threshold voltage needed for the special case inversion of 1.128 volts versus the ideal assumption that we originally had previously at 0.716 voltage. This concludes my homework assignment. Thank you very much.